In order to discuss relativistic Doppler effect, I would find it quite relevant to discuss classical Doppler effect, and we shall understand where we depart from the concept that relativity brings in. When an observer A is moving relative to the source S of sound wave, detects different frequency than the one emitted by the source. We all are aware with this Doppler effect. The frequency nu dash heard by the observer is related to frequency nu emitted by the source by formula nu dash equal to nu times u plus minus uo divided by u minus plus us. Here u is velocity of sound, uo is velocity of observer, us is velocity of source, and if both are approaching to each other, then the upper signs in numerator plus, in denominator minus is to be considered. Let us try hands on the formula. Let source emits sound wave at 1000 Hz. If the source is moving at 30 meters per second towards the observer who is at rest in the air medium, and the speed of sound wave being 340 meters per second. Then let us explore the formula. Upper signs we are considering. In the recap, we have equation on the left top corner. Nu dash equal to nu u plus uo divided by u minus us. So 1000 times 340 plus 0. Observer is in the state of rest, divided by 340 minus 30. After doing calculation, we get nu dash equal to 1096.7 Hz. If the source is at rest in the medium and the observer moves towards the source at 30 meters per second, the frequency of 1000 Hz source will appear as nu dash equal to, the formula offers us 1088 Hz. So here we get different result, even though the numbers are same, but the moving object is different. The other possibility in which relative speed between O and S is 30 meters per second such that each move towards other at 15 meters per second, which still offers different frequency. Now the observer is moving towards source with 15 meters per second, and source is also moving towards observer with respect to the air medium 15 meters per second. Now here we are charting that the medium is forming a frame of reference which is stationary, and we obtained 1092 Hz frequency. Here we have a situation in which it is not relative speed of the source and the observer that determines the Doppler shift. It is rather the speed of each other with respect to medium. This cannot be the case for light wave, since there is no medium. I mean, we have rejected the ether hypothesis, and no preferred frame of reference according to Einstein's first postulate. So what happens here? That's a question. We therefore require a different approach to understand the Doppler effect for light waves. An approach that does not distinguish between source motion and observer motion, but rather involves relative velocity between the two. Let us consider two frames S and S dash as usual with relative velocity v. Here bold letter V is charting velocity between two frames. The source is stationary in frame S and the observer is stationary in frame S dash. In the notations, I'm using bold V to indicate velocity, and nu should not conflict with that. Suppose the observer in S emits n waves at frequency nu. According to him, it takes an interval delta t0 equal to n upon nu. The corresponding time interval in S dash will be delta t0 dash, rather delta t dash, during which s dash moves the distance v delta t dash. The wavelength according to the observer in s dash is total interval occupied by these waves divided by number of waves. Lambda dash equal to therefore ct dash plus vt dash divided by n. And here from the formula delta t0 equal to n by nu, we can write n equal to nu times delta t0. So exploring that, we have c delta t dash plus v delta t dash divided by nu delta t0. Now that equation is appearing in the recap. Nu dash is equal to c upon lambda dash. Therefore nu dash equal to c times nu delta t0 divided by c delta t dash plus v delta t dash. So here you can take c delta t dash common in the denominator. C can be cancelled so that we are left with nu delta t0 divided by delta t dash inside bracket 1 plus v by c. So relativity offers us delta t dash equal to delta t0 proper time divided by under root of 1 minus v square by c square. That factor gamma is reflecting here. After substituting delta t dash equal to delta t0 upon under root, we have delta t0 to be cancelled and nu dash equal to nu upon 1 plus v by c inside the bracket under root of 1 minus v square by c square. For the quantity inside the bracket 1 minus v square by c square, we shall look for a square minus b square as a minus b into a plus b. By doing that, we have nu dash equal to nu divided by 1 plus beta under root 1 minus beta 1 plus beta. So this quantity can be taken into under root, it will be square, and 1 plus beta upon 1 plus beta 1 quantity we can eliminate and we can obtain a final formula nu dash equal to nu times under root of 1 minus beta upon 1 plus beta. Here in this formula we have already considered couple of things which we need to understand clearly. Waves are observed in the direction parallel to velocity. So wave should be propagated in the direction of velocity between two frames, observer and source. Note that unlike classical Doppler effect, relativistic Doppler effect does not distinguish between source motion and observer's motion. Rather, it depends upon the relative speed between source and observer. If the source and observer are approaching each other, then we use plus v, and in case they are going away from each other, we should chart it minus v. Now let us explore this formula. A distant galaxy is moving away from Earth at such a high speed that the blue hydrogen line at wavelength 434 nanometer is recorded at 600 nanometers, is redshifted in the spectrum. This is called as a redshift. It's going towards red. Find the speed of the galaxy relative to Earth. So the obvious formula is we are replacing nu by c upon lambda and nu dash by c upon lambda dash. So c upon lambda dash equal to c upon lambda under root of 1 minus beta upon 1 plus beta. So here we have all quantities except v, and we can tackle this equation for v in terms of c. That turns out to be 0.31 c. Thus the galaxy moving away, redshift causes moving away. Thus the galaxy moving away from Earth at a speed 9.4 into 10 power 7 meter per second. This illustration is based on the practical data indicating expanding universe in favor of Big Bang theory of cosmology. Now we are in position to understand the meaning of simultaneity for observers in different inertial frames. Let us suppose that we have two events for consideration, and these two events can be considered for two observers Once in frame S, Alice, and another in frame S dash, Bob, who is moving with competent speed comparable to speed of light. The two events for Alice in frame S are x1, y1, z1, t1 and x2, y2, z2, t2. So these events are defined by space coordinates and time coordinates. Similarly, for observer in S dash, the events are with prime x1 dash, y1 dash, z1 dash, t1 dash and x2 dash, y2 dash, z2 dash and t2 dash. Now delta t, that is time interval between two events, is t2 minus t1. Let us consider t2 to be a later event as compared to t1, and from Lorentz transformation equations, delta t dash, which is equal to t2 dash minus t1 dash, will be equal to gamma times the quantity in the bracket t2 minus vx2 by c square minus gamma times t1 minus vx1 by c square. So here we can work out the formula for delta t dash equal to gamma times t2 minus t1 plus gamma times v upon c square inside bracket x1 minus x2. I would advise students to pick up a piece of paper and really work out this. Is a simple. Now, if events are simultaneous in frame S, it means t2 must be equal to t1. Therefore, delta t is equal to 0. Then our formula tells delta t dash is not 0, in fact it is gamma times gamma times v upon c square into x1 minus x2. Now two events will be simultaneous in moving frame S dash also if and only if they are occurring at same location. That is, there should not be difference between the space difference between the occurrence of events, that is x1 must be equal to x2. Then and then only the events are simultaneous. Otherwise, they will not be simultaneous. So it is not necessary that the events will be simultaneous in S dash. For simultaneity to happen, we enforce that the events should not be at distinct places. Therefore, we conclude that simultaneity is not absolute. If the events are simultaneous in one frame, it is not necessary that they are simultaneous in another frame also. Now, to discuss meaning of mass in relativity, we shall develop a physical situation to write equations and tackle them in a meaningful way. Let us suppose that we have two objects A and B. The object A is thrown vertically down while B is thrown vertically up. The object A is stationary in frame S and the object B is stationary in frame S dash. Moreover, the usual contention that we have is S dash is moving along x-axis with velocity v. Now, with this contention, let us have a pictorial representation. We are observing the event from frame S. Now, with respect to our frame, object A is not having any velocity along x direction, it is stationary, and we are going to throw this vertically down. At the same time, the second object B, which is in frame S dash, which is stationary in frame S dash, is moving with respect to us along x direction, and when it is thrown vertically up in frame S dash, for us it will track a path indicated by the thin line. Now they are thrown with equal and opposite velocity, so that in the middle distance they undergo elastic collision, and after collision the object A will bounce back to initial position 1 and the object B will bounce back position number 3. The object A, which is stationary in our frame, is thrown vertically down from its initial position, as I have explained you in the diagram, with velocity v suffix a. This suffix a merely reminds me that the velocity is associated with the object A. The object B is traveling with uniform velocity v along x-axis and is thrown up at the same time with the speed vb dash. The dash indicates that the speed is being measured by the observer in frame S dash. It is related to the object B. So both objects A and B along z direction will track d by 2 distance. D, we have set up the distance between A and B along z axis as d. So both the objects, when thrown with equal and opposite speed, will track d by 2 distance along z axis to execute elastic collision. Then after collision at the half distance between them, they will return back to their initial positions as appearing in the respective coordinate systems. And for conservation of momentum, we can write ma into va is equal to mb dash into vb dash. So here, even though the proper mass of both the objects A and B is identical, their apparent masses are not identical. Now mb dash is mass of the object B as observed in the frame S dash. Now we can simply rearrange the equation for mb dash, and the equation will be mb dash equal to mava upon v dash b. So here the distance along z axis has nothing to do with the relative motion along x-axis. So in one case it will be d by 2 divided by delta t, and in the second case it will be d by 2 divided by delta t dash. Now after simplifying this, it will be ma times delta t dash upon delta t. So mb dash is equal to gamma times ma. So in general we can write m dash is equal to gamma times m0. m0, the meaning of m0 is proper mass. Here we are referring to proper mass of the object A in frame S, and mb dash is the effective mass of the object B appearing to the observer in frame S with reference to frame S dash. So m dash is equal to gamma m0. Now let us look at the quantitative effect that occurs in the mass because of the relative motion. The equation means that when the object of proper mass 1 kg moves with velocity 0.8 c, its mass will appear to be as 1.666 kgs for the stationary observer. Now here you can look at this table of gamma factor, and unit mass moving with velocity 0.8 c will appear to be 1.666667 kgs. When it is moving with further high speed, its mass, unit mass, will tend to appear as this quantity in kgs. For 0.69, 1 kg mass will be apparently 707 kgs and so on. Moreover, for any size of proper mass, that is non-zero mass, which is moving with speed comparable to speed or rather equal to the speed of light, its effective mass will be infinity because of this gamma setting in the multiplication. This statement itself suggests that the material particle cannot attain the speed of light, as it will absorb infinite energy for growth in its effective mass. Now we are going to deal with the most famous equation for which Albert Einstein is known to common people, that is mass energy equivalence. Let F bar is the force acting on a moving object of mass m and velocity v. This force will cause the gain in energy of the particle, and that is in the form of work done. That work done F dot dr, now we are writing as dt equal to F dot ds, where ds is displacement. Now we shall divide ds by dt and multiply so that the equation is conserved, and we shall replace rate of change of displacement ds by dt by velocity. So f dot v dt is the gain in the kinetic energy. According to Newton's second law, the rate of change of momentum is force. So here we can replace force by rate of change of momentum, and we cannot take liberty to consider m to be constant. Here mass is velocity dependent, and the parametric variable being time, we shall treat derivative of product of two functions as first function into derivative of second plus second function into derivative of first. So we have to replace f bar in this equation, and while doing so, the dt in the denominator commonly can be eliminated with this dt. So d capital T, the gain in the energy dt, is equal to mdv plus v dm dot v. So dv bar dot v bar will be v into dv. So mv dv plus v bar dot v bar will be v square into dm. This dm represents the gain in the mass due to velocity. Now we shall use another expression to explore the things. The effective mass, the relativistic mass, is equal to proper mass m0 divided by under root of 1 minus v square by c square. We shall square this equation so that the square root is eliminated, and we shall have cross multiplication so that we obtain m square c square minus m square v square is equal to m0 square c square. Now differentiating this equation, the exact differentiation of this equation, derivative of m square will be 2m dm. C square is absolute constant, which is the basic contention that we have started with, minus here we have product of two functions. The derivative of m square will be 2m dm multiplied by v square plus 2v dv multiplied by m square, and m0 is proper mass which will not change, it is independent of the motion. So m0 is absolute constant and c is also absolute constant. So we can eliminate common terms from this equation, and the common terms are 2m is appearing everywhere in the equation. So dividing the equation by 2m, we have c square dm is equal to v square dm plus vm dv. Thus we have two identical terms. So in the first philosophy we have the same quantity mv dv plus v square dm, and in the second philosophy we again have v square dm plus vm dv. Comparing these two equations, we can write dt is equal to c square dm. Therefore dt equal to c square dm. Integrating this equation over limits 0 to capital T, the mass will grow from m0 to the higher mass m, and integrating this equation, integration dt will be t upper limit minus lower limit t minus 0 will be t. Then integration dm will be m upper limit minus lower limit. We have m c square minus m0 c square. So energy E is equal to mc square. We are just rearranging this equation. E is equal to mc square equal to t plus m0 c square. So the total energy of the system E is equal to mc square we have established, which is equal to kinetic part plus rest energy due to mass of the object. Now in normal situations this mass is not converted into energy, but in some nuclear reactions we encounter with such a situation in which mass is converted into energy. Now in case the particle is at rest, the kinetic energy, kinetic part T is equal to 0. In that situation E is equal to m0 c square, that is the rest energy. Momentum of particle, P is equal to mass into velocity, and this mass is function of velocity and can be written by m0 gamma times v. So momentum, relativistic momentum of a system is m0 v divided by under root of 1 minus v square by c square. So here I am having same graph at our disposal which indicates gamma and v by c, which we call beta, on x-axis. So when we look at the momentum in a correct way, it should be gamma times the usual momentum. So gamma is a factor coming in the definition of momentum. Now m is equal to m0 upon under root of 1 minus v square by c square. So squaring and simplifying, we get m0 equal to m times 1 minus v square by c square, and multiplying both sides by c to the power 4, we have m0 square c to the power 4 is equal to m square c to the power 4 minus m square v square c square. I would advise students to pick up a piece of paper and write down these equations and really simplify to develop a feel. Rearranging this equation, m square c to the power 4 equal to m0 square c to the power 4 plus m square v square c square. So here this quantity m into v is relativistic momentum. Rather, this can be m0 gamma in place of m into v, whole thing square. So this quantity is relativistic momentum p, and this c is as it is. So m c square whole square is equal to m0 c square whole square is equal to p into c whole square. So this is one important equation in relativity, wherein we are replacing mc square by energy, the famous Einstein equation E equal to mc square. On right hand side, m0 c square is the rest energy, that is E0 square plus p square c square. So to remember this, I like to use the Pythagorean approach to understand, and the hypotenuse is the total energy of the system, and one side of the right angle triangle is rest energy, another side is momentum, relativistic momentum times c. Now in case c is equal to 1, so this equation will be E square equal to E0 square plus P square. E square equal to E0 square plus P square C square in case rest energy is 0. So we are talking about a massless particle, say photon, and when photon is not existing in the state of rest and the mass of the photon in the state of rest is 0, in that situation we have E equal to Pc and P is equal to E upon C, and for photon we write E equal to h nu from Planck's hypothesis, and the effective mass of photon we calculate as h nu by c square, and momentum of the photon as h nu upon c. Symmetry of time dilation is paradoxical. Let A is moving with respect to B, then B can equally claim that A is stationary and he is moving with respect to A in the opposite direction. This is the basic theme which, when explored with Lorentz transformation equations, leads to a claim that a moving observer can equally claim the other one is stationary and the moving clock is dilated, running at slower pace. This leads to a paradoxical situation. Question is, whose clock, A's clock or B's clock, is logging? And if we explore the relativistic equations, will lead to a paradoxical situation. Let us suppose that A and B are twins. A travels in a straight line at a relativistic speed to some distant location. A then deaccelerates and returns back. When A returns back to B, who is staying at home on Earth, now the clock associated with A will run at a slower pace with respect to B. At the same time, there can be a claim that A is stationary and B is moving in the opposite direction, and then in that case the clock associated with B should run at a slower pace. Therefore, there is a confusion that whose age is smaller amongst the twins, and it is difficult to conclude unless the reference is fixed. This paradoxical situation referred as twin paradox.